Right, let's get going with what we are going to do today. So last time I introduced the definition of a limit and of a partial limit. If you've done your homework, you've come in today and you have played with the equivalent ways of saying this, and you have rewritten these things several times. Once is not enough for most people. The amount of attention that you give to the stuff as it is coming to be ready for the next time you come into the classroom is worth 20 times as much as any study you do for a test. That's why my survival guide never tells you to study for a test. It says study to be able to walk into the class prepared. So what I really need you to have done is to work through these things over here before coming in today. And if you haven't yet, then please understand that this is because of the pressure from Monday to Wednesday, and you have to make up for it between Wednesday and Monday. And that makes the mathematics easier. I've got to make use of this material. I'm going to today begin by giving you some examples that illustrate these definitions. And in absolute horror, I noticed that I wrote the wrong thing in the text at this point. I pasted in from a green chapter into a yellow chapter and forgot to change the words. So I promise there will be a book update tomorrow morning. And in these two places, this is ridiculous. Maybe I should have just said X is a number. I think this would. Why is it capital? A number. Yeah. I think it's easier to read if I do that. Okay.
Sequence in right after that.
Yeah.
That after then is a sequence in big X. Example 2.
Sequence in a sequence. Everybody will know it means every sequence, unless otherwise stated, is a sequence of numbers. I'm sorry about that. This will be fixed. You see, in the green chapter, it had to say this. So I didn't notice that this had to be reworded. Very well. Finally, we can begin. A constant sequence always has a limit. This is the most boring of all the examples, but the boring ones are easy. Beware of the word interesting in mathematics. Here we go. We assume that x is a given number, and we are defining x sub n to be x for every n. And we're going to prove that this constant sequence that goes x, 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 x always actually converges to the number x. That the limit of this sequence exists. Actually, it turns out that x is a limit of the sequence, and it's the only limit. But anyway, here we go. Suppose. I don't know what to suppose. When I look at the definition, and then I look at the explanation, closer look at limits, the condition xn tends to x, which according to the definition says what? And there should not be one person in this room who would not be able to tell me instantly. This has nothing to do with whether you find math hard or easy. It's nothing to do with how hard this course is. It's not even to do with how good or bad I am, or how good or bad you are. But when you walk in today and I say, what do we mean when we say that x is a limit of sequence xn, you have to be able to tell me without hesitation for every neighborhood u of x sequence xn is eventually in u. And if you hesitate, that is for no reason other than you haven't done your homework. You see? It's not a matter of, well, I'm having trouble with this and I'm having trouble with that, and how do you solve the problems and how do you find the words and all of it. No, excuse me, that's you simply haven't done your homework, because you've got this definition, you come in today, it's got to be known. That's how a university course works, okay? Sorry to be tough with you, but I want you to make the stuff easy. So to prove this, you could say, I want to prove that for every neighborhood u of x something happens. But you could say, I need to prove that for every epsilon greater than 0, the sequence is eventually here. I have no idea. Which way should we do it? The two are so similar to each other, I have no idea. Should we take a vote? I don't know. Suppose that epsilon is greater than 0. Suppose that u is a neighborhood of x. Which way? Right? You said epsilon? Oh, whatever you take. Your word is law to me. Suppose that epsilon greater than 0, right? The condition x sub n belongs here holds for every n. Does it not? Because what's the definition of the sequence? Look, xn is always equal to x, which is smack in the middle of this thing, right? And well, take your big N to be 1. Do you understand? Right. You know, you really want to fuss? Define big N to be 1 if you insist. If you really want to fuss. You see? All right. Now, number 2. Every eventually constant sequence has a limit. We're given that x is the number and you've got a sequence, and that for some integer big N, the condition xn equals x holds from now and forever after. You see? Well, haven't we been told that sequence xn is eventually in singleton x? Huh? Right? In the previous problem, sequence xn was always in singleton x, you see. Now it's eventually in, right? Okay, here we go. Suppose that epsilon is greater than 0, right? We can see that for every n greater than or equal to this number big N, we have, how do you spell have? X sub n, which is x, belongs to that stick. Isn't that right? These are too easy. They're kind of annoying. Okay? Now we're going to come to exercise 4. What happened to number 3? I have no idea. It vanished when I wasn't looking, or maybe I didn't want to do it. I can't remember. Anyway, I'm doing number 4. Can't do everything. X sub n is 1 when n is even. I probably decided I didn't want to do number 3 because, you know, you open the text, you find another problem, but I think it was very similar. 3 when n is odd. So it goes 3, 1, 3, 1, 3, 1, 3, 1. Right? This sequence is a bit of a wobbler, is it not? Look what I wrote. I couldn't bear to write it, so I just put this here. If u is a neighborhood of 1, is it not true that xn belongs to u whenever n is even? Yes? How many even positive integers are there? Only 7 of them. Huh? Are there? Or are there infinitely many even positive integers? Okay? Infinitely many. Therefore, sequence xn, if u is a neighborhood of 1, then sequence xn is frequently in u. Do you understand? If u is a neighborhood of 3, then xn gets into u whenever n is odd, because then xn is exactly 3. Do you understand? So I've explained very simply that both 1 and 3 are partial limits of the sequence. Do you understand? And then I want to point out something. Let's suppose you have a number that is a real number. I'm looking for a picture. What happened to this? I know I stuck it in and it got lost. I wanted a nice little picture of a bit of number line. I know I had this. I must. Thank you so much. This is not to scale necessarily. Folks, look at this. Half the time the sequence takes the value 1 and the other half it takes the value 3. Do you understand? Now I'm not going to write this, I'm going to say this. I wrote it very briefly over there. But suppose that x is a number unequal to 1 and unequal to 3. Can you see the cases? Perhaps x is here, otherwise it is here, and otherwise x is here. So let's suppose x is down there. Isn't the stick from minus infinity to 1, the open interval, isn't that a neighborhood of x? For how many values of n does xn get into that? For how many values of n is xn there? None, right? Are there infinitely many values of n for which xn is there?
Only if 0 equals infinity.
Right? There are none at all, right? None at all, so there can't be infinitely many, right? Okay, let's suppose your number x is here. This open interval from 1 to 3, isn't that a neighborhood of x? For how many values of n is xn in there? For how many values of n is xn in that open interval? Look at the definition. Right? None at all, right? Are there infinitely many? No, there are none at all. There can't be infinitely many. And if x is greater than 3, use that interval. Do you understand? So what I said is that if x is neither of the numbers 1 and 3, then it's easy to find a neighborhood of x that doesn't contain 1 and also doesn't contain 3. Are you with me? Write it, please, folks. It's a very simple principle. I want you to then see that the number 1 is a partial limit of the sequence. The number 3 is a partial limit of the sequence. And no other number can be a partial limit of the sequence. Okay? That's what I want you to do. I will spend a bit more time on number 5. We are given that x sub n is 1 over n for every positive integer n. Every kid in Calc 1 knows that this sequence tends to 0, right? We're going to prove it. To prove that this xn approaches the limit 0 as n tends to infinity, we suppose, well, what is the definition? The definition says for every neighborhood u of 0, the sequence is eventually in u. Alternatively, for every epsilon greater than 0, the sequence is in the stick center 0 radius epsilon. I also told you that for practical purposes, when you're working with an actual problem, the epsilon and delta type of structure is a little easier than an abstract neighborhood because it lets you use inequalities. And please understand the statement that x is in a stick, the statement that a number is in a stick with a certain center and a certain radius says that the distance from that number to the center is less than the radius, all right? Okay, so I'll think I'll say suppose that epsilon, the epsilon is greater than 0. I'm putting it this way. Do you understand? Now, I need to, I'll change color and let me tell you what I'm thinking. I need to explain why sequence xn is eventually in the stick center 0 with radius epsilon. Do you understand? That's what I need to explain. What makes a number 1 over n get into that stick? I'll tell you, it's not going to be to the left. It's on the right side, isn't it? And there's no question that what you need is that 1 over n needs to be less than epsilon. Okay? So, yeah, so this is what we do. Choose a positive integer, big N, such that big N is greater than 1 over epsilon. That's, I think, what you were trying to say. See? And observe, whoops, and observe that 1 divided by big N is less than epsilon. Do you understand? Okay, now here's the important thing. For every n greater than or equal to big N, if you ever write for every n greater than or equal to big N, everybody will understand that you meant for every integer n greater than or equal to big N. If you feel like writing for every integer, if you put the word integer, it is more precise, but I'm going to tell you that the community would understand in this context, especially I'm going to refer to x sub n, it would understand that you meant an integer. If you have any queasy feeling, put the word integer in. For every, and I've left it in, I don't know whether I should have. For every n greater than or equal to big N, we can see that minus epsilon is less than 0. Reasonable? Okay. Less than the number 1 over n, because that's definitely positive. 1 over n cannot be more than 1 over big N, because look what kind of n I'm working with. N is greater than or equal to the big N. Is that reasonable? And we chose big N in such a way, how? That 1 over big N is less than epsilon, and there it is. So I have trapped 1 over n eventually into the stick. Is that okay? I hope that instrument, whatever it is off. Okay? Electronic devices, nowhere. Okay? Now, that's that one. I want to talk to you about number 6. X sub n is n for every positive integer n, and let me tell you what we want. We want to prove that x sub n tends to infinity as n tends to infinity. It's kind of weird. You know, it'd be like proving a theorem that as n tends to infinity, n tends to infinity. That's really what this is saying. It's kind of, it looks a bit silly, but let's check that it fits the definition. Now, what must you do? Well, I'm going to remind you. I'm going to scroll back. What was the statement about infinite limits? The condition xn tends to infinity. What does the definition say? For every neighborhood u of infinity, sequence xn is eventually in u. Alternatively, for every real number w, the sequence is eventually above w. Yes? I'm going to use this. It's a bit more concrete. How do you prove that for every real number w, the sequence is eventually here? In other words, eventually greater than w. How do you prove for every real number w? Suppose w is a real number. Yeah. So here we go. Suppose that w is a number. All right? Now I'll make it very simple. Choose a positive integer, big N, such that big N is greater than w. You see? And let me tell you that for every, the word integer is there whether you say it or not. Should I put it? I have no idea. For every n greater than or equal to big N, we have x sub n, which is exactly n, is greater than or equal to big N. And how is big N chosen? Above w. There it is, folks. We've just proved that this sequence tends to infinity. All right? I'm leaving number 7 for you, and I'm going to do numbers 8 and 9. I know that I must do 9. You will be petrified of it. So, okay. But I think 8 will warm us up. So here we go. There are shorter ways of doing these two problems that would be available after we've proved some basic theorems that everybody in Calc 1 knows. Every kid in Calc 1 has seen those theorems, but we are not allowed to use them yet. Okay, before I start this problem, I need to make a study of the number absolute value of n over n minus 3 minus, listen, you know jolly well from Calc 1 that you expect the limit as n tends to infinity of this to be 1, okay? Every kid in Calc 1 knows this, right? The question is to prove it now, you see? The question is to show how the exact terms of the definition of a limit lead one to be a limit of the sequence. That is the point. So don't ask me where did I get the 1 from. Every kid in Calc 1 would know you take this and you divide top and bottom by n, and you get 1 over 1 minus 3 over n, and that tends to 1 over 1 minus 0 equals 1. Every kid in Calc 1 can do that. The question is how do we show that this follows from the definition? I want to make a study of this because I really feel unable to begin this problem until I've made a study of that expression. So I want to tell you something about this. I'm looking at the absolute value, and I've got a fraction, and the bottom of this fraction is n minus 3, and the top of the fraction is n minus, okay, what? Well, 1, when you combine over a common denominator, 1 is n minus 3 over n minus 3. Isn't that right? So I just want to let you know that what I'm looking at here, on the top of the fraction, what have I got? 3. Just 3, yes? Don't need absolute value one. And underneath what? I've got the do we need, that's a good point. I'll tell you what, I better put it because I'm scared. But now I'll say, as long as n is greater than 3, any requirement I will ever make later in this problem, I will add to that requirement that n must also be greater than 3. Do you understand? If some big n comes along to help me, I will say, all right, I will take the larger of that and 4. Do you understand? I want to make absolutely, why do I say 4? An integer greater than 3. It must be at least 4. Do you understand? Why don't I say, well, let's take 3. 3 is terrible. You want to divide by 0? This thing doesn't even exist when n is 3. Better start at 4. Do you understand? I think that the very first thing I'd want to do in this problem and say, look here, I'm taking this sequence with the understanding that the domain starts at 4 and goes up from there because I don't want trouble. I don't want to live dangerously and put n equals 3 here and get burned. You see? So, okay. So as long as n is, should we say greater than or equal to 4, right? We have the distance between this and 1 is equal to 3 over n minus 3. Is that reasonable?
Except they have n greater than 5, or equal to 5 up there.
What?
As long as n is greater than or equal to...
4. I'm sorry. Well, it's also true if n is greater than or equal to 5, but I don't want to confuse anybody. Okay, folks? So this is what I'm going to tell you. To prove that that this sequence tends to the limit, what did I say? 1, right? As n tends to infinity, we suppose that epsilon or delta or something is greater than 0. All right? And I want to know that eventually, I'm looking over here. That's wrong. Where am I going? Here. The condition for xn to tend to x as n tends to infinity can be expressed. For every epsilon greater than 0, the sequence is eventually in the stick center x radius epsilon. Alternatively, for every epsilon greater than 0, the distance between xn and the number x is less than epsilon. Do you understand? That's what I'm looking at. And I told you that the inequality is usually easier than working with an abstract neighborhood. That's why I took an epsilon. So I'm going to ask myself, under what conditions will this be less than epsilon? Do you understand what I want? So I'm going to tell you the inequality that I really want that will say that this less than epsilon, this inequality requires what? That will hold when? You see, I'm still studying this. Under what conditions will 3 over n minus 3 be less than epsilon? Well, that will hold when I'm going to flip over n minus 3 divided by 3 is, you know what I'm writing? Greater than 1 over epsilon, right? Okay, multiply both sides by the positive number 3. You with me? Whoops, what'd I do? I'm trying to go there, right? And add 3 to both sides. This condition says that n is greater than some Charlie on the right side. I am now ready to begin. Here we go. Choose an integer big N greater than whatever this is. Just copy it. Choose an integer big N greater than that. Then let me tell you, whenever n is greater than or equal to big N, we have the distance between n over n minus 3 and 1 will be less than epsilon, because this inequality, that this distance less than epsilon, says that that is less than epsilon, and it definitely holds for all these values of n. Do you understand? That's what it is. I ask myself, what makes n over n minus 3 come close to 1? I looked at the distance from n over n minus 3 to 1, the absolute value of the difference, the distance. And I found that I'm looking at this as long as n is at least 4. Do you understand? Then I will say, okay, I'm going to choose an integer, by the way, this integer greater than this, can you see it will be at least 4? It's 3 plus something positive, and it's got to be an integer. It will automatically be at least 4. Good. See? Okay? Now, let me tell you something. As long as your integer is greater than this nasty number over here, the distance between 3 over n minus 3, the value 3 over n minus 3 will be less than epsilon. That's the distance between n over n minus 3 and 1 will be less than epsilon. So I've just proved that the inequality, this inequality that you see here, eventually holds for every n greater than or equal to the big N that I introduced over here. To look at this one more time, I said, first examine the distance from n over n minus 3 to 1. And we found that's the formula. Then I said, now, suppose that epsilon's greater than 0. How do I make this less than epsilon? Ask yourself, what makes this less than epsilon? Fiddle the inequality. Now you can see for which n's this happens. Right, choose an integer big N above there. For every n, at least big N, this inequality holds. That is exactly the statement that the distance from n over n minus 3 to 1 is less than the prescribed epsilon. That's how this works. And you've got a few more to get used to this idea. So let's look at this one. And it's just arithmetically a little bit more messy, but the method is exactly the same. This is what we do. For each n, we study the distance between this terrible looking creature and what? Well, listen. Go ask some kid in Calc 1 what the limit is of this as n tends to infinity. They all know that the limit is 2, don't they? I'll tell you how they do it. They say, next to the n squared term, the other terms are garbage. So don't write the garbage terms, and you've got 2n squared over 1n squared, and the n squared cancels, and this is 2. This is what they do, right? You want to be a bit more precise. The way you do it in Calc 1, you divide top and bottom by n squared. Okay? Divide top and bottom by n squared, and you get 2 plus stuff that tends to 0, divided by 1 plus stuff that tends to 0, tends to 2 over 1. You want to do something really stupid? Change n to x and use L'Hopital's rule. What an awful method. I mention this because some students like it. But the bottom of the fraction tends to infinity. You are allowed to use L'Hopital's rule on a fraction when what? When either both the top and the bottom are approaching 0, or what? Or the bottom is approaching infinity. I wish the calculus book said that. Anyway, mine does. Anyway, sometimes I'm not getting into this. Okay, section 5.3 VCT, if you have a VCT. So now, I am studying the distance between, what did we say, 2, was it? Okay, all right, let's have a look at this. Well, what we actually need is to combine over a common denominator, and so we are subtracting 2 times whatever it is over there. It's like this, is it not? Okay, and let's see what we have. Well, if you simplify what's on the top there, you find that you're looking at minus 5n minus 7. It's in absolute value, for heaven's sake. Do you mind if I pull out the factor minus 1? It's the same thing. All right? And at this stage, can I drop the absolute value because everything's obviously positive? All right? And so you might look at this in horror and say, eventually in this problem, I am going to say, suppose that epsilon is greater than 0, and I'm going to hope that for large enough values of n, this will be less than the epsilon. And you're going to look at this thing and say, it looks like an inequality from hell to try and decide when this will be underneath epsilon. Here is a strategy. Strategy. If you want to show that something is small, find something easy that's bigger and make the bigger thing small. I want to tell you something, that this is less than, if I drop those terms, I've put less in the denominator. This is bigger. Do you understand? I'm going to tell you something even more interesting. As long as n is at least 2, I know that 5n is more than 7. Isn't that right? Okay, so I've got news for you. If I come back to this expression, which is already known to be less than that, you understand? If n is at least 2, 5n is more than 7. So if I write, instead of 7, if I write another 5n, haven't I put more? I'm just being a little bit smart in putting easy looking things that are bigger above, and you know, something nasty and small is not as nice as something easy and bigger, as long as it's not too much bigger. See? So what are we looking at here? And by the way, I'm sailing by the seat of my pants here. I cannot guarantee that it says the same in the textbook, all right? I don't know what I did in the book. I never look. I always just go from the heart. I always tell people, one of the first rules of teaching mathematics, never mind what the math ed people will tell you, you listen to me. If you're going to be teaching mathematics, every lecture should be well prepared, but not too well. Not too well. You must actually be working the problem with your people for yourself. And never teach from notes. Always teach without having a clue how the problem works. And if you're going to struggle, let them see you struggle. Be brave. Is it a scary way to teach? It's the right way. It's the right way. So anyway, you know what I'm looking at here? I'm looking at 10n over n squared. It looks like 10 over n to me. So I've got a very nice, easy expression which is above the distance between this thing and 2. I'm now ready to start this problem, right? All this was just looking at the stuff that I need to go to do this problem. Suppose, I could say suppose that u is a neighborhood of 2. Nah, I told you, for the practical problems, it's easier to use a delta or an epsilon or whatever. Suppose that epsilon is greater than 0. Why suppose? Because we're trying to prove for every. You understand? Okay. Well, if you want to push this underneath epsilon, it is good enough to put this bigger thing underneath epsilon. Do you understand? So I want to tell you that the inequality 10 over n less than epsilon, that inequality will hold whenever n is greater than what? 10 over epsilon. It's just a matter of a bit of inequality, right? So I'm going to tell you now what I want. Choose an integer, big N, that is at least 2, because there was something about needing to be above 2. Do you remember? And is greater than 10 over epsilon. Do you understand? Now I can make a statement to you. I can say whenever n is greater than or equal to that integer big N, we can make a statement that this distance, which we know by all our smart inequalities is smaller than 10 over n, this now the fact that n is more than 10 over epsilon, that's going to be less than epsilon. See? So I've shown that this inequality, distance from there to 2 less than epsilon, holds eventually. We found a big N for which that inequality holds for every n greater than or equal to big N. And I continued. I've got some exercises here. And what I'm actually going to do is I'm going to do some of these. But what I actually think might be a good idea, and I'm not going to assign number 11. I know from bitter experience not to assign this one. I don't want to give you trouble. It's because of the snow. It's a really good problem. Give me a moment. Okay. Please note, number 11 not assigned, okay? And if you're not struggling in the course, do it anyway. It's a very good problem. It's a sequence that has tons of partial limits. It's a beauty, actually. Anyway. Yeah, question. Where?
Okay. Could it have been just as good when you got to the point that 5n plus 7 over n squared, just to knock out the n squared and say 5n plus 7 is greater?
I'm lost.
Yellow. You made it equal to 10n. Would it have not been just as easy to take away n squared and use 5n plus 7?
Or maybe just add 1n, or we have to add 5n.
Uh,
Well, you have to have at least 5n greater than
I want to write something that is more than that. Right? More than that. So I think, are you suggesting that I put a 1 in there?
Well, you can just use 5n.
But then you would have to start the n as being at least 8. You could do that.
I think, okay, well, then I have a question, and then
Yeah.
inequality to the right, where you said 5n plus 5n, could we have just said 5n plus 1n? That was
Yeah, that's what you're asking, and I understand your question, and you're right as long as you say it correctly. But I want to go back to Rick. I didn't understand what you said.
Okay, so when you get to the inequality for less than 5n plus 7 over n squared, obviously that's good. 5n plus 7 is greater than that as well. You just use 5n plus 7 and solve for n epsilon.
Oh, you mean don't bother to do this?
Yeah.
Then I could say, okay, down here, instead of this, I could have said the inequality 5n plus 7 over n squared holds, and then fish. But then you know what? It's more messy. There's an n squared and an n. It's a quadratic inequality. It's more messy.
what were you saying?
You see?
I'm talking about just the numerator.
It's harder.
N squared to 1?
Well, it's not just the numerator. You would have to write over here the inequality, and you'd have to be writing that instead of this cute thing, and asking when that holds. It's harder.
Well, I wouldn't use the n squared, just the numerator.
Say
There isn't. It's a whole fraction.
Well, you can say that is less than 5n plus 7 because you're dividing by n squared. Then I would just use 5n plus 7.
I'm not following you. You want to guarantee that this number is less than a certain quantity. I said find something bigger, make the bigger thing less than that quantity, then the smaller one will be.
So 5n plus 7 would be bigger than that, wouldn't it?
5n plus 7 over n squared.
I don't want to know that this is bigger than something. I want to know that it's smaller than
5n plus 7
something.
over n squared is less than 5n plus 7 over 1. That's what you're saying, right?
Yeah.
Over what? Well, then that's not small. You can knock, I'm not following what you're saying. But Nicole, I have to address yours. You don't like 5n. You want 1n. And then, when would that be valid? You would need to know that 1n is at least 7. So then you wouldn't start by saying that the n is at least, what did I say, 2 or something. You would have to start later in the sequence. And as long as you said that, it would be valid. Okay? But I just took the line of least resistance. I used the easiest inequalities. And I said, well, listen, I've got a 5n, and this here is smaller than the 5n. Let's have another 5n. That's inefficient, I know, but I was going for the easy rather than the efficient. Okay, so that's effectively what it is. Now, I want to do, some of these are very similar. I'm going to ask you to rewrite, but I think I want to do number 7. I'm going to make these fractions bigger so that you can see easily what we have. The formula for xn is sometimes 1 over 2 to the n and sometimes something else. And I want to show that this sequence tends to 0. The strategy is to show that when n is large, regardless of whether we're using the first formula or the second formula, the value xn will be close to 0. Do you understand? So I'm going to actually study these two things. First, note that if you look at 1 divided by 2 to the n, if you look at this, actually 2 to the n, I think that 2 to the n is more than n, isn't that? 2 to the 1 is at least 2, 2 to the 2 is at least 2 to the 1 is at least 1, 2 to the 2 is at least 2, 2 to the 3, don't you believe the bottom is at least n? It's a matter of simple inequalities. Okay, I would like to mention that 1 over 2 to the n is never more than 1 over n. Is that reasonable? Right? For each n. I'm looking for easy things that are still small, you see, but easy. And I want to hang on a second. Let me just write this. I wonder what that's less than. Well, if you don't put the plus 1,
Less than, right?
if you don't put the plus 1, haven't you put more in the bottom? So that's bigger? Well, I got news for you. If I don't put the square, then I'm getting that which is bigger again. You understand? So I've got news for you. We can make x sub n small by making 1 over n small. You see, this is not part of the solution to the problem. It's what I need to do before I begin so that I know how to do the problem. I'm changing color. Now I'm going to start the problem. I want to prove that this sequence has limit 0. Suppose that u is a neighborhood of 0, or suppose that epsilon is greater than 0. Which are we going to take?
Epsilon.
The epsilon. Suppose that epsilon is greater than 0. Okay?
Is it doable with the neighborhood?
Yeah, but it's easier when you're working in a concrete case to be working with inequalities than abstract neighborhoods. The first thing I would do with a neighborhood is I'd say choose epsilon greater than 0 and have all the extra steps. So I wouldn't do that unless somebody really begged me. Okay? Suppose that epsilon is greater than 0. So how do you make 1 over n less than epsilon? We've had this already today. You need n to be greater than 1 over epsilon. Okay? I think at this stage we can say choose an integer, a big N, greater than 1 over epsilon. You see? And observe that whenever n is greater than or equal to this big N, the distance between the number x sub n and 0, which is always, it's never more than 1 over n. Isn't that right? It's what we saw, regardless of which, you don't like 9, right? Okay. Regardless of which formula you're using, and 1 over n is going to be less than or equal to 1 over the big N, because I'm using n greater than or equal to big N, and 1 over big N, with the way in which I selected, the way in which I chose big N, makes 1 over big N less than epsilon, and there we have it. Okay, folks? So that even though we've got two different formulas, both are small. I squeezed both of them underneath 1 over n, and then I made the 1 over n squash it. Actually, there is a principle that you learn in Calc 1 called the sandwich rule, and I've really sneaked that sandwich rule into this problem together. Two people walking out together. I actually wondered, are they in this class? I've never seen them before. Ah, is that what it is? You mentioned that to me. Yeah, okay. Yeah, okay. Okay. So the fact is that I've sneaked in a proof of the sandwich rule here. Eventually we'll make it official. But there's a kind of hidden sandwich rule. We're squeezing the xn underneath 1 over n, and 1 over n tends to 0, so it squashes the xn to 0. That's really what's going on here behind the scenes. Okay, what's going on here? I love number 8. We have to do it. We've got a sequence of real numbers and a real number x. Prove that the following conditions are equivalent to one another. One of them is xn tends to x as n tends to infinity. The other says for every epsilon greater than 0, it looks just like what we had, except there's a 5 here. Okay, so I'm going to fuss. Are you ready? We assume condition A or B, I don't care which, make up your mind. You're going to assume one, prove the other, then new proof. I'll assume the other, prove the first one. Okay? Do you understand if and only if? Two theorems, two proofs. Okay? Here we go. I want to prove condition B. I want to prove condition B. What does condition B say? It says for every epsilon greater than 0. How do you begin a proof that says, of a statement that says for every epsilon greater than 0? Suppose that epsilon is greater than 0. Okay? I would like to point out to you the interval that runs from 0 minus 5 epsilon to 0 plus 5. What did I do? 0 plus 5 epsilon, that interval, isn't it? It's a neighborhood of 0. And so, look, what are we assuming? We're assuming condition 1. The sequence must be eventually in that neighborhood. Sequence xn is eventually in that stick. There goes from 1 to 2. In other words, 5 epsilon is a positive number. Therefore, the sequence is eventually in the stick, center, 0, radius, that positive number. Now we're going to assume condition B. I'll change color. We assume condition B. And we want to prove what? Condition A. All right. So we can begin. Suppose that epsilon is greater than 0. Or suppose that U is a neighborhood. This might be one time in my life I prefer the U. I will use the epsilon because you asked me, otherwise I will surprise everybody. Suppose that epsilon is greater than 0. You with me? The number, here's my problem. Condition 2 is going to tell me that eventually the sequence is there. It's not quite sharp enough. I need the sequence to come closer than that. Do you understand? So I'm going to do something clever. I'm going to say that the number epsilon over 5 is also positive. Okay? This number is also positive, is it not? All right. That number is positive. Using condition B, we choose big N such that the condition that x sub n belongs to the stick center 0 with radius 5 times that positive number. 5 times that positive number holds for every n greater than or equal to big N. Do you understand what I did? Read condition 2. Condition 2 says if you take a number, there's no law that says that the number has to be called epsilon. I'm calling it Charlie. Read condition 2. If Charlie is a positive number, then sequence xn will be eventually in the interval center x. Why is it? What made me write 0? Well, because we had 0 in the last few problems, so I got into the habit. Oops. Yeah, I'm sorry. The limit value is called x. I'm so sorry that where else? Yeah, I'm going to have to go through this whole thing again. Okay, because I forgot that the limit this time is called x, because in the last few problems it was 0, so I got into the habit of typing that. Okay, I'm starting over. We're assuming that xn tends to x. I want to prove condition B. Condition B says for every epsilon greater than 0, I said suppose epsilon greater than 0. The stick center x radius 5 epsilon is a neighborhood of 0, so the sequence is eventually in there. End of story. The first implies the second is too easy. Now we come from second to first. For every epsilon greater than 0, I'm guaranteed that the sequence is eventually in that stick, which on the face of it doesn't seem very good because the stick center x radius 1 epsilon is smaller. How do you know it'll be in the smaller one? This is the secret. Don't feel you have to call this number epsilon. Call it Charlie. If Charlie is a positive number, the sequence must be in the interval center x radius 5 Charlie. I now begin. Suppose that epsilon is greater than 0. I'm not interested in epsilon. The number epsilon over 5 is a positive number. There's Charlie. Condition B says eventually xn is going to be in the stick center x radius 5 Charlies, and the Charlie I have in mind is this number. You understand? I said using condition B we choose big N such that this holds for all n greater than or equal to big N. I am done. What is this? This interval is what? It's the interval center x radius epsilon, isn't it? There you go. You see, that's really the secret. Well, number 9 here is just like a problem I did for you. Yes, sir?
In the first proof, is it not supposed to be a neighborhood of x instead of a neighborhood of 0?
Well, where did I... Do you mean I've still got a 0 left in this? I thought I removed it.
The interval is a neighborhood of
I can't find it.
yellow. The last yellow line.
Of x. I thought I'd killed all of those. Right? You put it much too politely. Right? You should have said there's one more 0 that didn't come under the x. I'm sorry. You see, I read this problem thinking that the limit was 0, and I wrote it that way, not realizing the name of the limit is x. Why did I do that? Because in the last few problems, the limit was, actually, I don't know if it was. I think it was 2 last time. I don't know what made me. Okay, anyway, do you believe that by Calc 1 methods, the limit of this should be a half? Do you want me to help you with this one? I'll ask you next time. How about that? Is that a deal? Or I'll see what you send me. The method is first examine that minus a half, put in absolute value, and try and find something cute and easy and bigger. Something that you can squeeze to make small, and then that'll be even smaller. Smaller than small is small. That's the idea. All right, I won't steal this from you. I wish I could assign number 11. Now, I think I can start talking to you just a little bit about the notion of a tail, and then next time we'll do the tail about tails. So I want to give you a definition, and that's as far as we'll go. If sequence xn is a given sequence and big N is a positive integer, then the so-called big N tail, spelt that way, of the sequence is the set. It's a set of numbers, okay? It's the set. It's the set of the xn values that you can get for which n is greater than or equal to big N. That is called the big N tail. We have been already, in our definition and in the problems that we've been doing, we have been using the big N tail without calling it by that name. when we said that for every n greater than or equal to big N, something great happens, we've been saying that every number in that set does something great. Isn't it? You see? That's called the big N tail. Let me tell you a couple of things about these tails. The one tail of sequence xn is the range of sequence xn. It's the set of all the xn values that you can get. Isn't that right? What's the two tail? The two tail of sequence xn is the set of all the xn values that you can get by making n greater than or equal to 2. It's the set of the numbers. It's the set of the numbers x sub 2, x sub 3, x sub 4, dot, dot, like this. That's the two tail. Would you like to see what the 197 tail is? I'm going to ask you a question, true or false? The big N tail of a given sequence is an infinite set. So we'll do this in alphabetical order. False comes before true alphabetically. Who's voting false? Given a sequence, sequence xn, and a positive integer big N, this set here, the big N tail of sequence xn, is an infinite set. Who's voting false? I got one vote. 2 votes. I still remember I had this Math 4381 and there was this guy named Pedro. And everybody held their votes until they saw which way Pedro voted. There are also some cases here of some people who might be leading the way. I've got 3 votes, 4. How many? Let me see. All those voting false. I've picked up one more there, 2, 3. I've got 3 votes. 3 votes? Who's voting true? Well, the democracy certainly right. Of course, you haven't got Lewin's vote. I think I'm going to pick on Felicia here. Why did you say false?
Because when we did the two-tail, we said x sub n such that n is greater than or equal to 2, and we couldn't have greater than or equal to.
We couldn't have, so you've got the set of all the xn values for n greater than or equal to 2. That means you would have x sub 2 here, and x sub 3, and x sub 4, and x sub 5, and x sub 6. And you sure you still want to say false? Maybe you should stick to your guns. Maybe not. Given a sequence xn, given a sequence, I know we have to stop in a minute. Given a sequence xn and an integer big N, the big N tail is defined to be the set of all the numbers x sub big N, x sub the next integer after big N, which is big N plus 1, x sub the next one, which is big N plus 2, and so on forever. And I'm asking, must that be an infinite set? You want to change your vote? Stick to it?
Sure.
Stick to it? I'm not sure what you're thinking. I wish you would tell me. You might.
I don't think I'm
You're actually correct. You're actually correct. That's why I'm picking on you. All these people who said true or false or wrong, and you are right. Who else said false? There? And yeah, you guys are right.
I got the gut feeling it was false, but I didn't see it.
What if the sequence is constant? What if the sequence is constant? You know what this is? It's got only one number in it. That set does not have to be an infinite set because the sequence might have been constant. If the sequence is what we call a 1-1 sequence, that different ends give you strictly different values of x in, then sure this would be an infinite set. Okay? So I'm stretching your imaginations a little bit. I'm sorry to have teased everybody.
It's X2, X3, so I don't
You,
have to do
right? You understand why I picked on you? I thought you might say it's got to be the sequence might be constant, and I thought you might say that. And just in case you're going to say that, I wanted to reserve the moment to give you a moment of glory. You were nearly there. I wish I should have gone to the others, but I'm looking at the time, folks. That's it for today.